Go ahead, introduce yourself and what is your project?
Okay, my name is Joe Gonzalez. I'm a PhD candidate in Jim Anderson's lab in the Department of Chemistry, Chemical Biology. And what our lab really is not only studying current atmospheric chemistry problems, but we're at the forefront of studying how is atmospheric chemistry studied and how can we improve those methods. And our big objective is to develop tested and trusted actual forecasts of climate natural disaster risk. So for example, we know there's wildfires happening, there's hurricanes happening, but we have no trusted way of being able to just look at a certain set of conditions of the climate and be able to tell you there's a hurricane coming in 5 days. That's what we want to achieve. Why haven't we gotten there yet despite all the natural disasters? There's three fundamental issues we're solving. One, we don't understand how the different subcategories of how our climate runs are coupled together. The physics, the chemistry, the dynamics, the earth processes. You need a deep quantitative understanding of how those mechanisms and couples are very coupled. And then more importantly, you need state-of-the-art instrumentation that can directly measure both temporal and spatially in 3D all of those variables in the same volume space simultaneously.
And what is it going to do?
And then, or what are we going to do?
Yeah.
And what we're going to do is we're going to develop state-of-the-art instruments in aircraft together to be able to make the very first aircraft that can not only predict natural disasters, but straight up prevent them with very high certainty. We call this new aircraft SACOs. Stratospheric Airborne Comprehensive Observing System, sponsored by the Harvard's Lada Institute and Center for the Environment. You might ask yourself, well, don't we have satellites that can do that?
Yeah.
And absolutely, they can help us map long-term trends, but the main advantages of SACOs is one, we're gonna be 20 kilometers above the surface instead of 600 all the way in space. That's crucial because the return signal, the data to our computers, decrease as a function of square of the distance, which is why satellites, there's usually delays and corrections you have to make. So we're already going to gain 2 to 3 orders of magnitude in resolution just by being closer.
Awesome.
We're going to move slower at 30 meters per second instead of 8,000. So instead of only scanning the Amazon, for example, for like a few seconds, we're going to stay over it continuously, very slowly, giving us that high resolution temporal increase.
Awesome, thank you.
And then most importantly, to end, we avoid ionosphere interference. The ionosphere is filled with N2 and O2, which is known to ionize with the X-rays and high photons from the sun.